Now that we've learned how to name epoxides, let's talk about how you might go about preparing an epoxide. It says here, recall that epoxides can be formed when an alkene is treated with a peroxy acid. So if we take an alkene, like this molecule here, this is cyclohexene. So we have cyclohexene, right, because we have an alkene. So we take cyclohexene and we treat it with a peroxy acid. You're probably used to the structural formula for a carboxylic acid, which looks like this. So this is a carboxylic acid, and when we put an extra oxygen in here, we get a peroxy acid. So this is a peroxy acid here, and there are two commonly used peroxy acids that we use to make an epoxide. Okay, and the two most commonly used peroxy acids are MCPBA, which is metachloroperoxybenzoic acid, shown right here, and then also peroxyacetic acid. And so moving forward, anytime when we're making an epoxide, just like in this reaction shown up here, anytime we want to make this functional group, this epoxide, you could either put MCPBA or you could put peroxyacetic acid, and I would accept either one. And you're probably saying this is nothing new because you learned these reactions back in the alkenes chapter. But something that we didn't discuss before is that the fact that epoxidation of an alkene is stereospecific. And so you have to know that if you start out with a cis or a trans alkene, you're going to end up with a cis or a trans epoxide. And what we mean by that is, so you see here we have a cis alkene, the two R groups are on the same side. Well, when we form our epoxide, you can see that the two R groups are both on wedges, which means they're both on the same face of the molecule. If you were to draw a Hayworth projection of this, and I'll try my best here to draw a Hayworth projection with the epoxide coming out like this, you'd have the two R groups going up like this, and then the two hydrogens going down like that in your Hayworth projection. Also, if you take a trans alkene, so here you have the two R groups are on opposite sides of the double bond. Again, if you were to treat that with MCPBA or peroxyacetic acid, either way, you'd end up with an epoxide, and you'd end up with the two R groups trans to each other. And so that's shown here in this structure. And if we were to draw the Hayworth projection of that, again, I'll try my best here to draw a Hayworth projection, and we would have one R group going up like this and the other R group going down like this, the hydrogen going up and the hydrogen going down like this. And so the take-home message from this slide is about the stereospecificity of epoxidation, in that when you start it with a cis alkene, you end up with the two R groups cis to each other like this. When you start out with a trans alkene, you would end up with the R groups trans like that. Now we're going to look at a new way to make an epoxide. It says epoxides are also synthesized from halohydrins, and you should remember that when you have a bromine and a hydroxyl on adjacent carbons like we do in this molecule, this is called a halohydrin. And we learned how to make halohydrins way back in chapter 7. If you take an alkene like cyclohexene that we just looked at a few minutes ago, we take this and we treat it with bromine, we form the bromonium ion, but if we put it in water as a solvent, water acts as a nucleophile, and we end up with the halohydrin, and the bromine and the hydroxyl will be trans to each other on our six-membered ring shown here. So we've already looked at how to do that in chapter 7, but if you take that halohydrin and you treat it with sodium hydroxide, so just plain old sodium hydroxide, you can end up forming an epoxide. And this slide here shows us the mechanism of this epoxide formation from a halohydrin. First, the hydroxide deprotonates, so it takes the proton from the hydroxyl, and we end up forming an alkoxide. Here's our alkoxide, but what you notice is that the alkoxide is a good nucleophile, and you also have a good leaving group in the same molecule. And so instead of being an intermolecular SN2, between two molecules, this is called an intramolecular SN2 because the nucleophile and the leaving group are both on the same molecule. Now, something that's interesting here is that they've shown it here in a planar structure, but they've also decided in our book to show the chair form of the cyclohexane ring. And that is important because you should be fully aware of the fact that the alkoxide and the halogen, the bond to the alkoxide and the bond to the leaving group, have to be anti-periplanar to each other. So we'll put that in anti-periplanar. So in order for that SN2 reaction to occur, again, the bond to the alkoxide, or the bond to the oxygen with the negative charge, and the bond to the leaving group have to be anti-periplanar. So if you were to draw a sawhorse diagram, let's say you had, your alkoxide like this, and you had your leaving group like this. Now this is just a generic sawhorse representation. So if we had, the alkoxide act as a nucleophile, boom, and it's going to attack like this. I should put in some lone pairs, shouldn't I? We have our leaving group leave like that. That would work because these two groups, or the alkoxide, is anti-periplanar to the bromine if it was in another conformation. Now, if it was in another conformation, I'll just choose one. So we'll leave the bromine the way it is, like this. But let's say the alkoxide was here, like this, okay? Like this, okay? That will not work, okay? The SN2 reaction will not work. So not anti-periplanar, and therefore will not work. We won't get that SN2 reaction happening. And so the take-home message from this slide, again, is that the mechanism for the formation of an epoxide from a halohydrin is a two-step process. First, the proton transfer, then the intramolecular SN2 reaction, where the alkoxide bond to the alkoxide and the leaving group are anti-periplanar to each other. And so either route that we've learned to make an epoxide, both of these are stereospecific, in that if we use MCPBA, we start with a cis alkene, we end up with our R groups cis on our epoxide. And similarly, if we were to make a halohydrin in the first step and then treat that with sodium hydroxide, it is still stereospecific in that if our R groups in our alkene are cis, we're going to end up with our R groups still being cis in our epoxide. You should be ready to use either one of these processes at any time to make an epoxide. So halohydrin formation followed by treatment with sodium hydroxide to do an intramolecular SN2 reaction, or treatment with MCPBA, or if you don't like MCPBA and you want to use peroxyacetic acid, if you want to draw that out, that's perfectly acceptable too. Any one of these will work. With that in mind, let's take a look at some practice problems. 13.13 says identify reactants you would use to form a racemic mixture of each of the following epoxides. Well, we see in this epoxide here that we have the two phenyl groups. So we have a phenyl group here and a phenyl group here, and they are trans to each other with respect to our oxirane. And so we're going to have to start with an alkene that has those two phenyl groups trans to each other. So I'm going to think retrosynthetically here. If I had an alkene and if I had, the two phenols trans like that, okay? Well, that means that I'm going to have my methyl group up here, and then this proton, this hydrogen, is going to be down here. And so that would be my starting alkene. Now, what would the reagents be? It says here, identify the reactant. So we have the alkene. What would the reagents be? Well, you could either treat that with MCPBA. That would totally work. Or you could first make a halohydrin with bromine and water. That will work. And then in the second step, treat that with sodium hydroxide. And that will give you a racemic mixture of the product. Let's give the next one a try. You can see here that we have the two hydrogens trans to each other, and so we're going to have to start with some kind of alkene. Again, I'm thinking retrosynthetically here, where I have a hydrogen up like this and another hydrogen trans to it like that. Well, then you can see that the cyclohexyl group will be up here, cyclohexyl, and then we would have our methyl group down here like this. Now, what are the reagents? They're going to be the exact same reagents that we used in the first example. So I can literally just copy those in. So if I go copy, and I'll just paste those right in there, and that would be perfectly acceptable. And of course, that's going to give me the product that I want. All right, and if we look at this last one here, again, if we think about this retrosynthetically, we're going to start with an alkene. Okay, I'm going to start by drawing this hydrogen going up into the back on the right-hand side, and then I'll have my methyl down here. But when we have a ring coming off of one carbon like this, we call that a spiro ring. So this is spiro, or a spiro arrangement. And you can see that we have a 5-membered ring. So let's draw, right, it's a 5-membered ring. If we count 1, 2, 3, 4, 5. Okay, so 1, 1, 2, 3, 4, 5. There, we connect it like this. And if we count going 1, 2, 3, the oxygen should be where the number 3 is. So let's put the oxygen in there. So we'll just put an oxygen in here like that. Okay, so that would be our starting material. All right, and the same thing as before, we can paste in our reagents. So the same reagents that we used in the first two examples, and that will give us our desired product.